Hello, hi everyone. Welcome back to the channel. So, continuing in this binary search playlist, today we'll be solving this problem max median, which is a Codeforces div 2D problem, and this problem is also solved using binary search. And after you watch this video, uh, I'm sure that you would end up learning something new from this problem. So let's read the problem statement. So you're given an array A of length n. So we have an array which has a length of n. We have to find a subarray in this array A which starts at index L, which ends at index R, with length at least k. Its length, the length of the subarray, must be at least k with the largest median, and its median must be largest possible. Okay, that's what we want. Now let's understand a few definitions here. What is a median? A median in an array of length n. So we have an array of length n. A median is basically an element which occupies the position number this n plus 1 divided by 2, floor of n plus 1 divided by 2. After we sort the elements in non-decreasing order. So we have a bunch of elements, we have n elements. We sort them in non-decreasing order. We pick up the element at this position, that is floor of n plus 1 divided by 2, where n represents the total number of elements that we have in the array. This element is going to give me the median for that array. Let's take an example. Let's take this array which has 4 elements, 1 2 3 4, and let's see the median for this array. We can see that n is 4 in this case, and n plus 1 divided by 2 would be 2 for that case. That means the median would lie on the second position, and this is the second position. The median would be 2. Let's take this array, that is 3 2 1. It is not sorted in non-decreasing order. So first I must sort it in increasing order or non-decreasing order. It would give me 1 2 3, and n is 3, so n plus 1 would be 4. 4 divided by would be 2. 4 divided by 2 would give me 2. That is, the median lies on the second position. That means this one. This element is the median here. Okay, so it also says that, okay, if we have, if n is odd, if n is odd, then we don't require the array to be non-decreasing. It can be non-decreasing or it can be non-increasing. Okay, like in this case we had a strictly decreasing array, strictly decreasing elements. Middle element stays the same even if we sort the array in increasing order or in decreasing order. What do we mean by the subarray? What is a subarray? A subarray A which starts from L and ends at R is basically a contiguous part of the array A, okay, for some range L and R. So L and R lies in this range starting from 1 till n, and the length of this contiguous part is represented like this: R minus L plus 1. Okay, that's all. So I hope we understand what do we have to do in this problem. We are given an array A of length n. We have to find a subarray which has a length of at least k, but its median must be largest. So we want to maximize the median that we can get in this array. Again, maximize something. What is something here? Maximize median such that we can pick a sub array. We can have a sub array with at least length k, with at least, okay, so we got it. Maximize the median such that we can have a subarray with at least length k, and we want to find the median for that subarray. Okay, now n and k lies between 1 till 2 into 10 raised to the power 5, while the elements in the array cannot exceed the n, that is the number of elements which are present in the array, n, the size of the array. Okay, so we just have to output one integer, that is m, which is the maximum median which we can get. So let's better understand the problem statement using an example. So let's take this example. We have 5 elements in the array. The least the shortest subarray which we can take must have a length of at least 3, and this is the array. Okay, so let's see how we can find the median. What would be the maximum median which we can achieve in this case? So let's pick up all the possible subarrays. So the very first subarray is this 1 2 3. The median for this subarray is 2. Let's take the second subarray. Now we may have subarrays of length at least 3, so we can also take this subarray which has a length of 4, which starts from the first element. And even in this case, if we sort the elements, the array would be like 1 2 2 3. Okay, and we have 4 elements, and the median would be the one which is present at the n plus 1 divided by 2 with position, and that would be 2. So even in that case, the median would be 2. Let's consider the next subarray. Starts from 1 and set the last element, and if we sort the entire array, we would get 1 1 2 2 3. So an array of length 5 where the middle element is 2. So even in that case, you would have median as 2. Now let's start the subarray starting from the second element, and let's take this subarray. Starts from 2 and set 2. The median would be 2, because if we sort this array, we would get 2 2 3, and the middle element is 2. Let's take this array 2 3 2 1. Sort it 1 2 2 3. Middle element would be 2. Let's take this array, starts from the third element and set the last element 3 2 1. Sort it 1 2 3. That is going to give me 2 as the median. So we have explored all the possible subarrays which we can generate, which has a minimum length of 3. Now every subarray gives an answer of 2, so there is no way we can get an answer greater than 2. So 2 is the answer for this test case. Okay, so that's all. This also gives me the nice strategy to solve this problem, that is generate every single subarray which has a length k till n. So start from the first element, generate the subarray which has a length of k, find the median, again start from the same element, generate an array of k plus 1, or select an subarray of k plus 1 elements, again find the median, compare it with the previous median and update it. So in this fashion, keep finding the median for every subarray starting from every element which has a length k or greater. That is the brute force approach. But now sitting at every position and picking up and trying to find every subarray, it is very hard to create a working solution which will pass the constraints. Okay, that this type of solution, this type of brute force solution will give me TLE, or time limit exceed, that is generating every subarray of length k and greater than k starting from every index of this array. Okay, that is from 1 till n minus k. So this approach is not going to work. Okay, let's see how we can solve this problem in an optimal way. Again, let's focus on the answer. What is the answer? The answer is the maximum median. Let's call it m. This is m. We want to maximize this m. Okay, we want to maximize this m. Let's say m is the maximum median. which we can get for the particular test case. Okay, that means I will never be able to get m plus 1 as the median. I will never be able to get m plus 2 as the median because m is the answer. Won't be able to get m plus 3 as the answer, and so on. And take any median, it will never exceed n. It will always be less than equals to n. This is the range for the median in any case, in any test case for this problem. Why? Because observe that here, observe from the constraints that the elements in the array lies between 1 and n, where n is the size of the array. So that means the median will never exceed n. Hence the upper limit would be like n plus 1. We can never reach this point n plus 1. So I found the upper limit for the median to be n plus 1. So that's why it is important to observe the constraints in the problem statement, because sometimes looking at the merely looking at the constraints gives us the solution. Now, what would be the left extreme? We can see that if m is the answer, okay, if m is the answer, that is I can get m as the median. I can also get m minus 1 as the median. I can also get m minus 2 as the median, and so on till what is the left extreme? It is 1. That is here. So we have got the search space that is from 1 to n plus 1. We have this search space here, and or we can, let's say, write it 1 to n plus 1. This is the search space. Okay, and these are the medians which are possible to achieve. Let's call them good medians. Let's call them good medians. While these are the medians which are not possible to achieve, let's call them bad medians. Okay, again, now again the same wheel. What do we have to do in this problem? Binary search over this median. We have the range, find the middle element, let's call it mid. We got to check if this mid lies on this side or it lies on this side. If it lies on the good side, that means, let's say it lies here, mid is here, then that means this can be my potential answer, while I may have a better answer in this range. So update the range, the search space, to mid plus 1 to high. While if it lies, let's say, on the bad side, let's say here, then obviously we can't have our answer on this side. The answer would lie on the left side. So update the range to low to mid. Fine. So in this fashion I will end up calculating this m when I will have only one element remaining in the range, and that has to be m. Okay, now in this fashion I will calculate the m, but the main challenge is to find whether this mid lies on the good side or it lies on the bad side. How can we do that? Let's see. So observe in the problem statement we are given that we can take subarray of minimum size 3, subarrays of minimum size 3, and in that subarray we want to find the median. Now since I have guessed the median to be mid, what I want from this array, all I want from this array is that if there is some subarray which exists in this array which has median at least mid. Okay, so that's what we want, which has a median at least this mid. How can we find that? So the most naive solution would be just start traversing this array. Let's take the very first subarray of length k, then we have to sort this subarray, and for that we have to maybe copy all these elements in a temporary array, then sort that temporary array and find the middle element, and so forth. That's the usual naive solution, which is going to take a lot of time and space, and it is not very optimal solution. So here we have to use a trick. So observe and pay attention carefully. The trick that we are going to use, the trick is very simple. What is our target? Think about what do you want here. All we want is just to check. We have already guessed the median. We've already guessed the median to be mid. Now all I want from this array is that just tell me if I can get this mid as the median in any of the subarrays such that the length of those subarrays is at least k. That's all I want from this array. That's the information which I want. Now let's modify this array little bit. We already have this mid, and let's create another array. Let's call it array B for this array A, and put one element. Let's put one for all those elements. Let's call it AI, which are greater than equals to mid, and let's put -1 for those elements in the array B which are less than mid. Why we are doing this, you will understand it. So let's replace them. One, let's say the guessed mid in this case is 2. Let's say we guess 2 as the mid. Mid is 2 here. Now this is less than 2, put -1 here. This is greater than equals to mid, put 1 here. Put 1 here, 1 here, -1 here. Now I have my B array prepared. Okay, I have my B array prepared. Now how this array is going to help me? Observe that if I take a subarray of size k in this array B and sum up all these elements. Let's sum up these elements. -1 plus 1 plus 1. It is going to give me 1. So what does this tell me? It tells me that the number of elements in this subarray which I have chosen, the number of elements which are greater than this mid, the number of elements, let me write the count of elements, this count is greater than the number of elements which are less than mid. That's what this positive integer represents. If it is positive, that means we have more ones in this subarray, and this is only possible if we have more elements which are greater than equals to this mid. Fine. Okay, so I hope you are getting where we are going. So now take any other subarray. Let's take this subarray which has a length of 4 and sum up all these elements. We would get -1 plus 1 plus 1 plus 1, that is 2. That means we have more number of elements which are greater than equals to mid than the elements which are less than the mid in this subarray of length 4 starting at the first element. That means since I want to return just yes or no from this function, from this array, all I want, because we have already guessed, what I want is it possible to get this mid? Obviously it is, because we are getting 1, we are getting 2 which are positive integers, means we have subarrays which has at least length k such that the elements in that subarray, the count of elements in that subarray is which are greater than this mid is greater than the count of elements which are less than this mid. Like in this array, we have 2 elements which are greater than equals to mid, we have 1 element which is less than mid. Hence, if I find the median in these kind of subarrays, that median would always be greater than equals to mid. Okay, obvious conclusion. So that's all we want to do. That's all we would do. Let's say the next step. The next step. Now let's, okay, so how can we do that? How can we find how can I just ensure, how can I ensure in this array B that I always find a median which is greater than equals to this mid? For that, let's calculate the prefix sum. Since I want the sum of all elements, let's, because I have chosen this subarray, I wanted the sum of this subarray. I choose this subarray, I wanted the sum of these elements, the sum of these minus ones and ones. So let's calculate the prefix sum. The prefix sum would be minus 1 plus 1 would be 0, then it would be 1 here, it would be 2 here, it would be 1 here. This is the prefix sum which I have builded over this f. How this is going to help us? Let's see that. Now we want subarrays which are at least of length k. Okay, k is 3 in this case. So the very first subarray would be this, and it ends at this position. And what I can see here is that I have 1 here. I have 1 here. That means the subarray of length 3 which ends at this position has median greater than equals to this mid for this subarray. Let's move to this position. Let's move to this position. Now the subarray which I want to choose, maybe this may now the subarray, now what are the subarrays which I can choose while I am standing on this position? That would be these subarrays, this one, this one. These are the two subarrays which I can choose. Okay, so standing on this position, what I am saying is, if I choose the subarray of length 4, then the number of elements which are greater than equals to mid are 2. Fine. So what I would do here, I would find the minimum prefix sum from position 0 till position I minus k for every position I. Why? From position 0 to position I minus k, I will find the minimum prefix sum. What does that minimum prefix sum represents? The minimum prefix sum represents the, let's say the minimum prefix sum is minus 1 on this range. What does that represent? It represents that, let's say the minimum prefix sum lies at this position j, this position j. Then let's say I'm standing on ith position, then the subarray that I'm gonna take would be this one, from j to I. This subarray will ensure me, this subarray will give me the most optimal subarray. Why? Because till this point j, I already have the minimum prefix sum. That is, I already covered the maximum number of elements which are less than mid. So from j to this point I, the number of elements which are greater than equals to mid, it is more chance that we have more such type of elements in this range from j to I. Why? You can take an example and understand it better. Valid. Okay, now the problem boils down to finding the maximum sum which we can achieve in this subarray B. In this array B, the maximum segment sum which I can achieve in this subarray B. That's all I want. And the minimum length necessary is k. So we want to take segments of length minimum k, and we want to find the maximum sum which we can achieve. So that's why I've computed this prefix array, and now the problem is simple. Let's start from the kth position, and kth position for this is 3. So start from kth position. All I want is for all of positions starting from 0 till I minus k. So I'm standing on position number I, this is I, and for all these positions what I'm going to take is I'm going to take the minimum prefix sum. I'm going to take the minimum prefix sum. So I is 3 here, I minus 3 would be 0, this one. So from 0 to 0 I'm going to take the minimum prefix sum and it would be minus 1. Okay, and now from the sum which I have on the ith position, which represents the sum from the very first element till that ith element, that's what this sum is representing. I'm going to subtract from that sum, from this entire sum, this minimum sum that we have achieved in this range. And for this we have 2 minus minus 1, that is going to give me 3. That means the maximum sum segment which I can achieve till ith position is 3, is of 3. That's the maximum segment which I can achieve. That is the case here. I choose this segment and the sum here is 3. Okay, so I want to maximize the positive sum. That's why standing on any location I just find the minimum prefix sum from 0 to I minus k and subtract that minimum prefix sum from the sum which I have on the ith position. That is going to give me maximum sum segment. That's very obvious standard sliding window algorithm, we can say, or a simple implementation or a simple application of prefix sums to find the maximum sum segment over a subarray. Okay, that's the problem boils down to basically. Fine. Now let's implement the solution which I discussed here. Okay, so this is a max median function which takes in this array A, the segment length k, find the lower bound, find the lower limit, higher limit, it would never cross n plus 1, run the usual binary search. Since I want to find the last true element, I want to find the last true element, find the middle element, check if it is a valid. If it is valid, then that means the range would be reduced to mid plus 1 till high, while this mid can be the potential answer. Otherwise the range will be reduced to low to mid minus 1. Fine. So in this fashion I would find my last true element, which will be stored in this L, and I will return it from here. This is just an application of the last true which we discussed in the first video. Let's see the implementation of this check function, which is crucial for this problem. So this is the check function which takes in this array A, the m or the mid which we have guessed right here, this one. I'm passing this mid here and that's what I'm receiving here. Find the size of the array, declare another array B of the same size n, and prepare this B array like this. If I have any element in the array A which is greater than equals to m, assign 1 for that position in array B, otherwise assign -1 for that position in array B. Find the prefix sum, build the prefix sum over this array B, okay, to find the maximum sum segment. Then start iterating from the kth position, okay, and the maximum, the prefix sum till this position would be b of k minus 1. Now this mx represents the, this mx basically represents the maximum sum over the segment, over any segment of this array, of this prefix sum. This represents the maximum sum which we can achieve over this array B which I prepared here. That's what this mx is stored. So till the kth position, so before I, so for the very first segment of length k, the maximum sum would be this, that is b of k minus 1. That's the maximum sum till this position. Now let's this mn represents the minimum sum. Let's say we are standing over any position I, then this mn will store the minimum prefix sum which I builded over this array B, that is minimum for this B from position 0 till position I minus k. That's what this is going to store. Okay, so this mn will simply store what? The sum at the ith position minus the minimum sum here which I obtain here from position 0 till I minus k. Okay, so minus this, so I minus this is what this mn variable is going to store. So I iterate from the kth position till the last position, find this m, okay, find this mn. Okay, so what does this mn will store? Mn stores this value, that is this one, that is minimum sum from 0 till I minus k for any position I. That's what this mn is going to store for me. So let's start iterating from position number k. So for any position I, find me the minimum sum from 0 to I minus k, that I get simply like this. Update this mn with bik I minus k, then update this mx variable. How? Bi minus mn is going to give me the maximum sum over any segment of this array B. How? We discussed it here. How I got the maximum sum over this subarray range. So in this fashion I will have my maximum sum which I can achieve, the largest sum which I can achieve, okay, for this array B, which simply represents, now if this largest sum achieved mx is greater than 0, that means yes, we can achieve this m as the median. So I return true from here, otherwise I return false from here. Okay, so I hope you are getting where we are going. So we simply use this technique, that is storing -1 and +1 for the numbers which are less than mid and the numbers which are greater than mid, which made our life a lot easier. So these type of techniques comes only with practice. That when we solve more and more problems, then we are capable of coming up with such solutions during the contest. Okay, so let's see the time complexity for this solution. Now the time complexity for this implementation would be n log n. It is n log n. N represents the range is from 1 to n, and this n is for the predicate function, because I am iterating over this array A once here, then once here, then once here again. So n counts for that complexity. So n log n is the overall time complexity, while the space complexity used is also big of n. It's not constant, it's big of n, because I'm using an auxiliary array B which I am building over the array E to store the prefix sums. Fine, now that's all. Let's jump to the code implementation part. So this is a solution class. Let's implement the max median function, max median, which takes in this array A and which also takes in this integer k. Find the two limits. The left limit is low, that is 1. Higher limit is a dot size plus 1, and iterate over this range. Low is less than high. Find the middle element, that would be low plus high minus 1, high minus low divided by 2. Check if it is valid. So pass in the mid, pass in the a, and if it is a valid range, then update this low variable to this mid, otherwise update this high variable to this mid, and at the end return this low here from here. Then from this, now create another function, let's call it check, which takes in this mid and the array A. Now here initialize another array. First find the size of this array A dot size, which is n. Initialize another array B, which has a size, so iterate over the array A. For every element which is greater than equals to mid, assign 1 for that position in array B, otherwise assign -1 for that position in array B. Then prepare the prefix sum. So prepare the prefix sum over this array B. So B of I is nothing but B of I minus, this is how I compute the prefix sum. Then let's initialize two variables, max variable which stores the maximum sum segment, which stores the maximum sum over any segment, and initially we store this value here. Let's take a min variable which stores the minimum from 0 till I minus k. Now iterate over the elements starting from k till end, and update this max, update this min with this value, that is I minus k. So this simply gives me minimum in 0 to I minus k, that is minimum sum which I can get, while mn is going to give me the maximum sum, which simply mx will store the maximum sum, that is max of this already existing sum, and the current sum is bi, while the minimum sum in this range is mn, which I have already computed. That is going to give me the maximum segment sum from 0, let's write it, maximum segment sum from 0 to I. Fine. Now at the end return if this maximum sum which I got is greater than 0 or not. If it is greater than 0, return true, otherwise return false. So this is how this function is working, and this is the implementation in C++. Let's see the implementation in other languages. Okay, so this is the implementation in Java, and this is the implementation in Python language. So that's all for this video. If you like the video, then hit the like button and continue with me in the binary search playlist. We are about to end this series in a couple of problems, so stay with me. I hope to see you all in my next video.